Hello everyone, in this lecture we start chapter 4 and we are going to study the Reynolds transport theorem. So this theorem is a general theorem that allows us to understand the transport of any fluid parameter and see how those fluid parameters evolve in time, and we can find a formula for that, for the differential form of any change in a fluid parameter. That can be mass, that can be velocity, or any parameter, right? And then after that, we are gonna generalize. So first we are gonna look at this 2D case, a simple two-dimensional case. And after that, we are gonna look at the general form of Reynolds transport theorem, which will be a 3D case. And this will be kind of the Reynolds transport theorem that we need for this course. And we will use this theorem to derive some of the conservation laws of fluids in the next chapter, which are conservation of mass or continuity equation, and also the linear conservation of linear momentum in fluid flows, and we will derive those in the integral form first, and after that we will briefly touch on the differential form of these conservation laws in any fluid flow phenomena. Okay, so we need this Reynolds transport theorem in order to be able to drive those conservation laws. So I start with this simple example and simple figure that is shown here. So here we have a fixed control volume of flow, and I will define what is a control volume. And this is a very important phenomena because we will deal with this phenomena a lot in this course. So this blue, if you have like a fluid that is going between these two plates, so it's go from left to right. Okay, so this blue line that I have kind of drawn here is, we call that as a fixed control volume, or sometimes we call it CV, or control volume. Okay, and this is a volume in space, and it's steady, right? So a volume, so for example, in any fluid phenomena, for example, if you have a pipe flow, if you have a channel flow, you pick a fixed control volume in space, and that then you will write the conservation laws or any theorem for that specific fixed control volume. Okay, so this is how we approach different fluid problems. Okay, so this blue line, say this blue is at time t. Okay, and then say this fluid that is inside this volume is gonna move, right? It's gonna move with time. It's gonna go to the right, right? So I show the fluid at time t plus 1 with a red line. So let's see how the fluid evolves at time t plus 1. So at time t plus 1, the fluid flow in this volume goes a little bit to the right. Okay. As you see here. Okay. So this red is at time t plus delta t, okay? So now let's see, I want to define some stuff. So here, first of all, here, this is the volume of a fluid. Let me so I call this volume at here as 1, that I have drawn these gray lines, gray hatches, okay? And then the other one, I'm gonna also call this one here, this volume, I'm gonna call this volume 2. Okay. And the rate that this, the first one, let's say, or the second one, what is this length? Can you think about it? If you want to kind of think about and estimate this length, we have the velocities here. This is V1 and this is V2. And also we know the time step is delta T, right? So this length, which I call it as delta L2, should be what? Should be V2 times delta T, right? Why? Because V2 is, the definition of velocity is length per time, right? So delta L2, and this is how much we have gone at time delta T plus delta T, right? So this length should be delta L2 should be V2 times delta T, right? And that is what I've written here. Okay. So similarly, I can write it for this length here. I call this delta L1, I name it delta L1, which equals to V1 times delta T. Okay. So let me write this a little bit bigger. Okay, so this is the configuration, and now I want to make some definitions of this transport of fluid in this kind of configuration. Okay, so first definition that I want to define is system. So a system at time t is a control volume CV, right? So it's control volume CV, which is essentially this blue line that we have here, right? So that is what we call system at time t. This is our system. This can be a fluid system or any other system. Okay, so it's a very general theorem. It's kind of a mathematical theorem that we are using it in fluid context. And then we have system again at time. What is system at time t plus delta t. Well, what is the system at time t plus delta t? Okay, so the system is going to be this red line, and I want to show it as the sum of the things I have kind of indicated in this figure. So it's going to be CV, which is the original system. Okay, the original system minus the volume of 1, right? So this one, system 1, say, and then plus the new volume that is added to the system, which is going to be 2, right? So this is the system at time t plus delta t. And then another definition I want to make is if any fluid parameter. So a fluid parameter is defined as follows. So I want to make the definition for extensive and intensive parameters, fluid parameters. So B, capital B, equals to mass times B. Okay, so any parameter that has this mass in it, it is called an extensive parameter. And this B is an intensive parameter, which is independent of mass. So anything that is independent of mass, any fluid parameter, is called an intensive parameter. Okay. For example, we can say B, which is an extensive parameter, equals to M mass times V, where V is velocity, okay? And this is going to give us, this is what we call momentum of the mass. Okay, so B, for example, this B, intensive parameter, which is a parameter independent of mass, can be anything. For example, it can be velocity, okay? And so this is, for an example of that, for example, if you put velocity, B is going to be momentum of mass, and it's going to be, capital B is a extensive parameter, and V is an intensive parameter, okay? So now I want to write any fluid parameter that an extensive parameter for this system, okay, for this system of fluid. It can be, it's a very general thing. It can be velocity, it can be acceleration, and it can be any other parameter. It can be other things, right? So temperature and other things. So at time t, B of system at time t equals to, based on this definition that we had here, equals to B of the control volume at time t, right? And at time t plus delta t, B system t plus delta t equals to BCV t plus delta t, right? Minus, I just write these in terms of mathematical operations that I've defined, and also the definition of a fluid parameter, okay? It's anything, can be anything, minus B at 1 time T at T plus delta T plus B of 2 at times T plus delta T, right? This is what we have here. I just wrote it down, and this is the control volume, CV at time T, and then the red one is CV at time, and then we have the CV, the CV is the blue one, okay? And then we have this B1, which we are gonna subtract from the CV, and the green one, which is 2, that we are gonna add to the system, and this is the system, kind of the condition or situation of the system at time t plus delta t, okay? So now, based on these definitions, general definitions, very simple kind of definitions that we made, I want to find the time rate. So find the time rate of change of this, okay? So the time rate of change of system is going to be delta B system over delta T equals to B system at T plus delta T minus B system T over delta T, right? This is just a definition of that. So let me put it a little bit to the left. This equals to B from here, B system at T is what? Is BCV at time T. Oh, sorry, first I have to write this one. So B system at time T plus delta T is BCV at time T plus delta T minus B1 T plus delta T plus B2 T plus delta T and minus BCV T, right? This is just from here, I just substitute everything of this equation here from the definitions that we had before. This over delta T, okay? So now I can divide this into two expressions. The first one is BCV T plus delta T minus BCV at time T over delta T minus B1 T plus delta T over delta T plus B2 T plus delta T over delta T. Okay, I just rewrote these and kind of rearranged the terms. So now in the limit, let's take the limit to get the differential form of this. In the limit that delta T goes to 0, let's see what would be the rate of change of this system. This B, again, B is an extensive parameter that can be anything, right? For example, mv is the momentum of mass. We can put like t or acceleration and anything. Okay, so let's take the limit. So the limit of BCV t plus delta t minus BCV at t, at time t, over delta t equals to, what is this? If you remember your calculus, this is exactly the definition of derivative. The derivative of BCV with respect to time, right? So this is just a derivative of BCV. And what is BCV? Is what it is MB, right? This is the definition we made here. So this is definition. I just write it down. So instead of B, I'm gonna put BM. So this is the derivative of BM with respect to T. Okay, and instead of M, I wanna write rho delta V, rho V, right? Rho V, which is gonna be the rho times density times volume. Okay, and I'm gonna get that across the whole CV. So say for example, for all the elements, I'm gonna, if you have like a small dV, which is the volume, right? The mass of that, the mass of dm is gonna be rho times dV, right? So let me show it again, or another way to say that. Say this whole B is kind of composed of all very small elements like this, which we call it dm, and then I'm gonna get the integral over the whole CV. Okay, so I want to write it as integral of, which is integral is just a sum of all the small elements dm over dt equals to d, and instead of dm I'm just gonna write rho, which is rho is constant, say it's constant, and then rho times dv, right? Because rho density is dm over dv, so I can write instead of dm rho times dv. Okay, so it's gonna be the integral over the whole control volume of b times dv, where v is volume here, over dt. Okay, so this is volume. Okay, so this is the first term. And then let's look at this one. This 2, this section 2, we call this outflow, and this 1, we call this inflow. Okay? So the outflow, for the outflow B2, or the outflow B2, I can write B2 at T plus delta T equals to M2 B2, okay, which equals to, this is just a definition of B, right, capital B, which is M times B, which equals to rho 2, M, I just write rho V2, rho delta V2 times B2. Okay, this is the volume. So this is gonna be, this is the whole volume of that. We just call this delta V2. Again, this is volume. This is different than this V, which is velocity. Okay, just remember that. In order to distinguish that, I just add a line here. B2 equals to, so the volume is what? Let's look at that. So the volume, if you have like a, it's a 3D flow. So the volume is gonna be, say, if this has an area, let me just show it here. It's a 3D flow, and let me just maybe show it here like this. If this has an area like A2, okay, so the volume of 2 is gonna be what? It's gonna be delta L2 times A2, right? This is gonna be the volume of the outflow, okay? So let me just write it down. So instead of delta V, I'm gonna write rho 2 delta L2 times A2 B2. And instead of delta L2 based on here, I'm gonna write V2 times delta T. So this equals to rho 2 A2 V2 times delta T times B2. Okay? So similarly, for inflow B1, we have B1 at time t plus delta t is gonna be rho 1 A1 V1 delta t times B1. Okay? So, what we have learned so far is we have this rate of change of B, which is any parameter in the system. So I just write this delta B over delta T as T delta T goes to 0 is nothing other than this derivative of B with respect to time. So I just show it with B dot. Okay. And also B dot of out, this is how much B goes out, which we find from here, out of what? Out of this control volume, right? So this is how much B is going to out of this control volume, which is calculated as the limit of delta T goes to 0 of B2 T plus delta T over delta T, right? This is nothing other than this term. Which equals to rho 2 A2 V2. Let me write it down again. From here, I just put it here. This rate of change is going to be rho 2 A2 V2 B2 delta T over delta T. So these two are going to cancel out. And so I have rho 2 A2 V2 B2. Okay? And similarly, the amount of B that is coming in or inflow is going to be rho 1 A1 V1 B1. Okay? So I can now rewrite this equation here in terms of these things that we found out. So dB, or derivative of system with respect to time, dt, equals to equals to what? Equals to all these individual terms, right? So this one is gonna be dB cis over dt, right? As you take delta t. So we have this on the left hand side, which is as you take the derivative as it goes to 0, we just get this, right? Okay, let me see if I can do it this way so you can see it. So we have this term here. Just follow this as I write it. It's just all these terms here. So it dB cis minus of dt equals to the second term, which is this term. And here we show that this term is equal to this, right? So I'm just going to write it down here. Equals to. So the total derivative of B system with respect to time equals to the partial derivative of B system, or BCV, the control volume, with respect to time plus this term, which I've put it here, right? Or I can just write it down as B dot out. So plus B dot out minus this term. What is this term? It's just B dot in, right? Okay. So this is very important formula. And let me just rewrite this B dots in terms of these things that we found. So the total derivative of B in the system with respect to time is the partial derivative of BCV with respect to time plus rho 2A2 V2 B2 minus rho 1 A1 V1 B1. Okay? So let me emphasize on this. This is a very important formula. And this is what we call, this is Reynolds transport theorem under some assumptions. And we will look at a more general form of that in a moment. Okay, the 3D form of that, the more general form of that. But I just want you to think about it physically. What does this mean? This is a very simple formula. This means that the total change of a parameter, a fluid parameter in a system, equals to the local change of that parameter in a given fixed control volume, which can be this one. Let me show it maybe with this color. The change of that in this system. Let me write it down here again and explain it again. So let me see if I can copy this. to here. So let me try to explain it here so you better understand what this means. Okay. So this means the rate of change of any extensive parameter in the system, okay, equals to the local change of that the local change of that parameter in a fixed control volume, say this blue one, partial BCV over partial T, okay, plus the change of that parameter for the outflow, which is this green one, how much that is changed for this outflow, B dot out, and minus how much it is coming in. Okay. So this is the rate of change of the system at time t. Okay. And this is gonna be very intuitionally, you can understand what does this mean, right? So this is just from this perspective, when you look at the flow in this coordinate system for with a fixed control volume, you can write this equation, which is going to be the local change of any fluid parameter plus the change in the outflow minus the change of the inflow that is coming to that new control volume. Okay, and this shows the total change of the system. And why it is not just a partial change of that, of the CV, it's because you also have some inflow and outflow, right? So you cannot just look at this blue one and see how much it is changed here, but you should also look at the inflow and outflow that is coming in and goes out of your system, right? So for example, this much has come into the system and this much has gone out of the system, right? So we have to consider for those in order to get the correct change of the total change in the system. Okay, so this is the whole idea of Reynolds transport theorem. This is a very simple theorem. It's actually the main reason we use that is to kind of convert this total derivative to this partial derivative and with all the changes that we need, right? Okay. And in a 3D form, this will find a very interesting form that I'm going to show it now. So, and that's why we use this Reynolds transport theorem. So let's look at this in a more general way. So the topic now is general. Look at this, the general form of this, the general form of Reynolds transport theorem. Okay. So in 3D, three dimension, we look at the amount of property B carried across the area element delta A in time delta T. Okay, so what does this mean? Let's look at it. So here we had a one-dimensional case, right? And how does this look like in a 3D form? So in a 3D form, say we have a area element like delta A as like this. Okay. And then this is the normal vector to this area. N is normal vector. So this is the surface element area. And then the velocity vector is not necessarily normal to the surface, right? It can be different. So this is V, or velocity vector. And these two make an angle of theta with each other. Okay. So now we write this Reynolds transport theorem for this surface element. So delta B is defined as B delta M. This is the definition we had already, right? B is M times B. So delta B is going to be B times delta M. And this equals to B times, if the density is constant, B times rho V, where this is volume again. And this is going to be B times rho times, instead of delta V is going to be delta A, which is this delta A that I've shown here. So this is delta A. Let me show it again. This is delta A. Okay, so this delta A times delta Ln, which is the new change in the fluid, but in the normal component, right? So how much you go, for example, in this direction. Say you go this much, this is going to be delta Ln, and then you multiply that by delta A, and you will get this volume here, okay? This is going to be the delta V. Okay, so let me clean that. So this is going to be B rho delta Ln times delta A. This is going to be delta V. And why I only look at delta Ln, the normal vector, is because we are interested in things that go across these elements, across these area elements, like here, right? So whatever goes across this is what we are interested in, and not whatever like goes here, like parallel to that. We are only interested in what goes across that, so we should only look at the normal vector. Okay, so let me write this down here. Since across element delta A, we look at the normal component. Okay, because if, for example, this is an area, I want to know how much the fluid is moved in this direction here, to understand how much fluid has gone across this delta A element, right? So I don't care about if the fluid has gone this way, right? Because it's not going to cross that and go across this delta A, right? So I'm just only interested in how much of it goes outside, because I want to see how much goes into or outside of the control volume that I have considered, okay? So what is this delta N? Delta Ln is what? Is gonna be the V times cosine theta times delta t, right? So instead of V delta t, which we had before, is going to be V times cosine theta, because we are only interested in the normal component of the velocity along this surface, right? So if you look at it, this is going to be the normal component of the velocity. This is V times cosine theta, right? This one is V times sine theta, and the other one is V times cosine theta. So therefore, if you multiply that by delta L, delta T, this is going to give us the delta N, delta L on the normal component of delta L, right? So delta B is B rho. Instead of delta Ln, I'm going to write V cosine theta delta T and then times delta A. Okay? And the rate delta B dot is going to be the limit of delta T goes to 0 of B rho V cosine theta delta A delta T over delta T, and these two are going to cancel out. So I only have rho B V cosine theta delta A. Okay? So now I want to define something that you have probably learned in your algebra, and that is dot product. Okay, so just for those who might not remember that, we define dot product. So the dot product of two vectors is defined as follows. So V cosine theta, we define, let me write it the other way. So the dot product of two vectors, like V dot N, is V cosine theta, right? So this is the dot product of two vectors. So V dot N is going to be V cosine theta here, okay? And so this is the definition of dot product, which is defined for two vectors. And this is like how much you kind of project one vector into another one, okay? And see how much of that vector is in the same direction with the other one. So now based on this, I can rewrite delta B dot as rho B, instead of V cosine theta, I'm going to write V dot N delta A. Okay? So, now let's see the total outflow. So total outflow for a control surface, or CS, is defined as follows. So the control surface is also a fixed surface in the space. So B dot out, which we had for a one-dimensional case was defined as this. This was B2, and B dot out was this, defined as this. So for a three-dimensional case, this is going to be the integral over the control surface of out of delta B dot out. Okay, what does this mean? This means, for example, here we don't, if you have a surface, okay, so you took the delta B for all these small elements, and then calculate, this is delta B out, and then calculate the change over this surface. Okay, this is what we call control surface, this one that I have shown here. So they take the integral of the change over this control surface of out, right? So I write this control surface of out. This is control surface. Let me show it again. So this is the control surface of out, and this is gonna be the control surface of in, which comes in, right? So this is control surface of inflow, what is coming in into this control volume, and what is goes out of this control volume. Okay, so delta B dot equals to, and I have this delta B dot here, I just write it down. It's going to be the integral over the surface, control surface out, of rho B V dot N dA. Okay? So this is B dot out. And then similarly, total inflow on the control surface CS in is as follows. So it is B dot in, which equals to, and because this is inflow, and this is one definition that, and this is kind of a convention that we define here, and you can follow this convention. And the convention is when something goes out, okay, out of any control volume, that has a positive kind of sign, but when it goes into the control volume, that has a negative sign. So when it goes out, we write this as positive. V dot N is positive. And when it goes in, right, when it goes in, this is N, and this is V. And here, let me show it. So this is N, and also this is V. So V dot N is positive here, but for when it comes in, V dot N is going to be negative, right? So we will have, I need to add a negative sign for that, for an inflow, okay? So let me write it down here. So it's minus integral of over the control surface in rho B V dot N dA, and so this is the convention we have. Normal vector is always toward out. This is our convention. So we have negative sign for inflow. So to clarify this, for outflow region, this is our convention again. For outflow region, so for outflow region, this V dot N is positive, as I showed you, because they are kind of parallel to each other, because the normal vector is always out, and this is what we always define for a normal vector in fluid and in controlled volumes that we, as a convention, we consider. Okay, so for outflow region, V dot N is gonna be always positive because this is outflow, and inflow region, V dot N is gonna be negative. And it's clear again, I show it again here, just to remind you again. So V dot N is always, let's say if we have something like this, normal vector is always defined outward, okay? So here and here. So if you have an outflow which goes out of a control surface, so this V dot N is gonna be positive, so this is outflow. And then if you have, say, this inflow region, which the fluid is coming to this control volume, so this black one is CV, control volume, fixed control volume. So here V dot N is gonna be negative, right? Because they have different signs, okay? So this is inflow region, and this is outflow region, right? Fluid comes in here, goes out here to this control volume. So this is the convention we use for these problems. So now let's calculate the net flux. So the net flux or flow rate. So flux is what? Is just a flow rate. When I call flux, when I say flux, I mean flow rate of parameter B across the entire control surface is as follows. So this was for the control surface of out, whatever was going out, and this was for whatever was coming in, right? So for a control volume, say you have a control volume like this, okay? So some part of it, for example, the flow can go out, and this is we call control surface out, and some of it, the flow can come in, right? And this we call control surface in, okay? So for the entire system, if we want to see what is the net flux, is it going out or is it coming in total for the whole control volume, what do we need to do? We just need to subtract B dot from B dot in from B dot out. So B dot out minus B dot in gives us what is the net flux of that controlled volume across the whole control surface of this. So it's going to be the integral of C control surface out of rho b v dot n dA minus the integral of control surface in, I just rewrite this here, in, so sorry, I have to write it like this. This is going to be minus, I have one minus here, which is from here, and then b dot is also negative, so it's going to be minus the integral of Cs in rho b v dot n dA and interestingly, what does this mean? This means this is going to equal to the integral of Cs out plus Cs in of rho bv dot n dA, right? Because this is going to be plus. Right? So what is the control surface of out plus control surface of in? It's just the total control surface of your control volume, right? So it's going to be the integral of control surface rho b v dot n dA. Okay? Very interesting formula. And recall from previous derivation, I just rewrite it here. We had this formula, so we had dB cis over dt equals to that. I just copied here, dt right? I just write this from the one-dimensional case, okay? So BCV is the integral now over the whole control volume of BDM. This is what? This is again the sum of small elements equals to the integral over the entire control volume of rho, instead of dm, I just write rho b dv. Okay. So based on this formula, dB system the total derivative of B of system with respect to time equals to the partial derivative of the integral of the control volume rho b dv plus all these terms b dot out minus b dot in, which is what? Which is here, which is this. I just write it down here. Plus the integral over the control surface of rho b v dot n dA. Okay? So this is the 3D version of Reynolds transport theorem. And this term, as you see, is the change over the volume. We first calculate the change over the volume, and then this is the change over the surface. Okay, so this is important. This means that the total change of any parameter in the system equals to the change of that over the volume, the control volume, plus the change of that over the surfaces. Okay, so this is what it means. So for example, if you have any control volume like this, okay, so this means that, for example, any fluid parameter, and then you have fluid that any fluid parameter, the total change of that in the whole system equals to the change in a fixed control volume here, how much it is changing in that control volume, plus how much it is going out or in to the surfaces, from the surfaces. So for all the surfaces, you have this, like this comes out, this goes in, right? So you calculate this over these surfaces, okay? And that's volume. So this is the Reynolds transport theorem that shows the total change of any parameter in the system. How can it be represented at the partial changes? Partial changes. And so we call this, for example, B. For example, for mass, this can be for mass, this B can be mass, momentum, energy, etc. Right? So this is a general thing. This B is a general parameter. So for example, let's set B as M, mass, to derive. So we will do this to derive the continuity equation in integral form. So I will do this in the break, after the break. So we will set B to M, which is mass, to drive the continuity equation in integral form. And so we will use this formula to find all these conservation laws, as I said, like continuity, momentum conservation, mass conservation in fluids, okay? Also, in advanced level, you might hear that we call this the Reynolds transport theorem. For example, in a fluid context, we call this Lagrangian and Eulerian view of fluid flows, right? So you might hear that later if you do advanced fluid mechanics, but I just wanted to give you idea. This is coming from this the same principle that you have learned so far, which is this Reynolds transport theorem. So let me briefly overview and review what we learned today. So we started with showing the Reynolds transport theorem in one dimension for a simple case, which is a fixed control volume. And we showed that, for example, we have this control volume at time t, and then at time t plus delta t, we have this fluid or this control volume is moving to the right because of the flow motion. And then we define the fluid parameter B as an extensive parameter, which is mass times an intensive parameter. For example, B could be, small b could be velocity, or it could be even 1, which then B is going to be the mass. And then we can get the continuity equation. And then we wrote the change of this B system at time t based on this simple case for a one-dimensional case. We calculated the limit of change of this delta t as this goes to 0, and then we wrote this also for outflow and also inflow. So this is b dot out. We found that it's going to be this, and then for inflow this is going to be this. And then we wrote this Reynolds transport theorem for a one-dimensional form with under some assumptions, which is dB6 over dt equals to partial BCV over partial t plus how much flow goes out, b dot out, the flux out of the system minus the flux into the system. And then we derive this for a three-dimensional case. So for the three-dimensional case, the difference is we are going to define the normal vector over a surface, and then we are going to get the integrals, take the integrals over area elements. So we took the integral over the area elements, CS out and CS in, and based on the definition of dot n, this was the b dot in, the normal vector. And so we calculated the net total flux or flow rate of parameter b across the entire control surface, which these two sum up together, and then this will be the total, the integral of rho bv dot n dA over the total, over the whole control surface. And then we use the same formula for one-dimensional case, and then we got to this 3D or general form of the Reynolds transport theorem, and this shows that the change of any variable, any parameter in the system, for example, this could be mass, it could be velocity, this could be momentum, this could be energy. The total change of that with respect to time, the derivative of that equals to the change of that over the control volume plus the fluxes that are going out or in, the net flux rate or the net flow rate into the system, okay? Which is the integral over the control surface. Okay, so in the next session, after the break, I'm gonna set the B to M, to mass, to find and derive the continuity equation, conservation of mass, and then after that, we will solve one example and try to find the linear momentum equation later on.